Hello, welcome to this short training offered under the CISA project Sustainable Energy Solutions for Africa. My name is Dr. Albert Alponi. I am a senior lecturer at the Department of Electrical and Electronics Technology at the Kington Apiaminka University of Skills Training and Entrepreneurial Development in Ghana. In this video, we will review the PV sizing process, and then we will go through an exercise to design a PV standalone system. You learn in the Unit 2, Lesson 2 of this unit that in designing a PV system, there are about 6 steps. It does not really matter the order in which this is done, but it is important to begin with the load study that must be done. Then you select the voltage for the system. Then you size the components, the PV, battery, inverter, and select the charge control. The major components of a solar PV system are the solar charge controllers, inverter, battery banks, and load, of course. And this needs to be selected according to the system type, the site location, and the application. In this exercise, we are going to consider a typical house with the load requirements as indicated. And the task is to design a solar PV standalone system to meet the load requirement. This system is located in Kumasi, Ghana, and the PV module specification has been provided. Now, in the next slide, I will be taking you through the first procedure, which we said is to determine the total energy demand. Of course, this step is very important because when it is not done properly, it can lead to either oversizing or undersizing. Oversizing of the system would lead to waste or redundant components, extra cost, while undersize will mean not being able to provide the energy demand. Now, here we are going through this exercise in determining the demand using a table. In this table are provided the appliances in the first column and their power rating. For the lamps in the task, we're given 2 lamps, 15 watt each, fans, 2 of them, 40 watts each, TV 1, 68 watts, and satellite 1, 17 watts. And the hours of usage were also provided. So to get the demand, you multiply the wattage, the total wattage, times the hours of usage. So the total demand for this house was calculated at 895 watts. The next thing to do is to determine the system voltage. But the system voltage is also really important. In fact, all the steps I keep on saying are important, but the system voltage is important in the sense that for standard components such as the battery, the PV, many of them are rated 12 volts. However, it is recommended to have a high voltage in some situations, because with a high voltage you will have low current in the system, which will minimize the voltage drops. And however, that will mean that you will need to have more batteries in series, more panels in series, and therefore will add to the cost of the system. The guideline usually is that you make sure that the steady current drawn is below 100 amps. And usually the suggestion I give in the design process is to just look at the AC power. And if the system power is below 1200, you can go ahead with a 12 volt system. If it is between 1200 watts to 240 watts, you can go in go in for a 24 volt system. And when it's above 2400 and to 480, 48 watt system, and when it's a large system, you may have to consider higher voltages. This is the suggestion that I normally recommend. This our system, the wattage rating is below 1200. Therefore, our system voltage will be 12 volts. Let's now continue by sizing the PV modules. To find out the sizing of the PV module, the total peak produced need to be determined. The peak produced depends on the size of the PV module and the climate of the site location. Usually, the PV ratings that are indicated on the panels are determined under standard conditions, that is, installation of 1000 and temperatures of 25 degrees Celsius. The actual amount generated by the panel will not exactly be the same as the rated capacity. This is because the conditions at the site where the panel will be used will definitely not be the same as the standard 1000 installation and 25 degrees Celsius. In Ghana, for example, where this exercise is being done, the temperature is always above average about 30 degrees Celsius almost throughout the year. We have to correct for these variations from the standard conditions. This is done by calculating the panel generating factor, which I sometimes refer to as the efficiency of conversion, to account for this variation. In fact, corrections may include 15% for temperatures above 25 degrees Celsius. So when the site is located in areas like Ghana, where the temperatures are always above 25 degrees Celsius, you will consider 15%. You consider 5% for losses due to sunlight not striking the panel straight on. Here in a typical domestic situation, the panels will be roof mounted. They will not be tracking. Therefore, this loss needs to be considered. 10% for losses due to not receiving energy at maximum power point. However, when the charge controller is a maximum power point tracker, this percentage can be ignored. 5% allowance for debt, 10% allowance for panel being below specification and for aging. These percentages are assumptions, and the amount that we use will depend on the particular location. So therefore, the total power here is going to be equals to the product, that is 0.85, that is to account for the temperature, times 0.95 to account for the 5% losses, 0.90 times 0.95 times 0.90, and that will give us approximately 0.62. So you now need to multiply this by the daily sun peak hours. The daily sun peak hours can be obtained, and there's a lot of resource data on that. I have taken this data from NASA website for Kumasi, the location where our hypothetical case is located. And in doing that, you need to pick the month with the lowest insolation. Here we have August having the lowest insolation of 3.920. So this is what is going to be used for sizing our system. So therefore we can go ahead. Our total daily energy requirement was calculated as 895. We divide that by the daily peak sun, and I'm saying here that we select the month, the meant with the lowest peak daily radiation, daily peak sun hours, then times our conversion efficiency. Here we are taking the value of 0.62. Therefore, the PV size required is 368 watts. To get the number of panels required, we divide that by 110. 110 was the specification given in our task. So we will have about 3.3. So approximately we require 4 modules in our system. So now that we've gotten the number of modules required, we will continue with our exercise, and this time we will go on to size our battery. The battery type recommended for use in solar PV system is usually the deep cycle battery. Deep cycle battery is specifically designed to be discharged to a low energy level and rapidly recharge or cycle charge and discharge day after day for years. So they are normally recommended for PV systems. The battery should be large enough to store sufficient energy to operate the appliance at night and at cloudy days. And so to size the battery, the procedure usually is to calculate the total watt hours per day used by the appliance. And you need to also consider the days of autonomy. That is the number of days the battery should be able to operate on its own before receiving a charge. This, as I said earlier, will be able to account for cloudy days. Then we need to look to also know the efficiency of the battery and the depth of charge. Usually for deep cycle batteries, 0.20% is the minimum depth of a charge. Then the battery voltage of the system. So our load here is 895, and we are assuming 1 day, that is 24 hours of autonomy. The battery efficiency of 0.80, that is 80%. Then the depth of recharge in 12 volts. So we will require 466.2 amp hours capacity. So the battery bank should be rated 12 volts, 500 amp hours for 24 hours autonomy. We now need to pick the correct size of the inverter. The inverter must have the same nominal voltage as the battery. With the size, it should be at least 30% more than the total watt of all the appliance. This is to ensure then we go ahead to charge this to size the solar charge controller. The solar charge controller is typically rated against the current and the voltage capacity. You select the solar charge controller to match the voltage of the PV array and batteries. The current rating of the charge controller, just like in the case of the inverter, should be at least 30% more than the short circuit current of the PV system. So in this case, we could have 4 strings of PV panel, and each one has short circuit current of 7.15 amps. Therefore, when you multiply that, you will times 1.3, we have 39 amps. So the charge controller that we needed should be rated at least 40 amps at 12 volt or greater. In conclusion, what we have done today is to follow the procedure for sizing PV system in undertaking this exercise. What we learn is that to size a PV system, you need to first of all determine the energy requirement. Then you decide on the voltage. Then you will look at the PV size, calculate the PV size, but you must consider the correcting factors. Then you size the battery, the inverter, and select a charge controller. There are a number of software, some of them public domain or commercial, some of them commercial softwares for PV sizing and for doing this exercise. I will entreat you to go through these websites for further studies, and this will help in understanding this. Thank you so much. I'm happy to respond to any questions, and I'm available through this. Thank you so much.